Alright, so in this video we're going to learn about conservation of energy looking at a mass in a spring system. So let's say that we have a frictionless surface with a wall, and attached to it is a spring, and it's just at rest at its natural position, and it has a mass on it. And let's say that the spring constant is 100 newtons per meter and the mass is 2 kilograms. Okay, so we would call this position x equals 0. It's the rest position of the spring. Now, if I were to stretch the spring out, so I apply some force and pull it in this direction, now there is some change in position, that's some positive x value. Let's say that it's 2.5 meters. Alright, now if I pulled this and I have now stored elastic potential energy in this spring, it's at rest, but it has the potential, if I release it, to start moving in this direction and starting to convert its energy to kinetic energy. Now if I release the spring, or release the mass, it's going to start sliding in this direction, and it's going to gain speed, it's going to pass through its original position and continue in this direction. So when it is back at its original position here, where x equals 0, it's going to have some velocity, right? Because it has gained speed from here, where it's at rest, where velocity equals 0, and it is going to take all that elastic potential energy and convert it to kinetic energy. Now, as it goes back this direction then, now the spring is pushing back in this direction, trying to slow the mass down. And when the mass gets to a position that is equivalent to minus x, or minus 2.5 meters, that is when it's going to regain its EPE, its KE is 0, and it's going to stop again and slow down. So this system should continue oscillating back and forth if we store energy in it by extending the spring. Now, in the next unit, we're actually going to talk about oscillations, so we'll come back to this again. But for now, let's just do an example where we actually calculate the conservation of energy. So let's start by figuring out what is the velocity at this position. So in this case, we have all elastic potential energy when we've stretched the spring out to position x, because the velocity is 0, and then we release it, and that elastic potential energy completely converts to kinetic energy. So I can say that the 1/2 kx squared is equal to 1/2 mv squared. And then I just have to plug in. So 1/2, the spring constant I said was 100, x is 2.5 squared, that's my displacement from original position, plus 1/2 times 2 times v squared. Right? And if I plug that in, you can see I've done that here already. I get 17.68 meters per second. So at this position, we're going 17.68 meters per second. Okay. Now, if I were to continue in this direction, I would slow down, and then I would come to a velocity of 0 here, and then I would continue back to the right, and I would return and still have 17.68 meters per second at this position. Now, let's also figure out possibly what is the velocity when we're not at our original position. Let's say, what is the velocity, and I'll just draw it here, when the mass is halfway back. So let's say where, in this case, x is equal to 1.25 meters. Okay, and we'll say it's just going in this direction, but it could be going in either direction. So we have the change in elastic potential energy from here to here is going to be the kinetic energy gained. So we have some EPE here, initial, and we have some EPE here because the spring is still extended. But the difference between these two is going to be how much kinetic energy is gained. Okay? Remember, it's just a tipping scale. It goes from one type to the other. So we just really need to figure out what is the difference between these two elastic potential energies, and that will be equivalent to our kinetic energy at this position here. So we'll just say the 1/2 kx squared at the beginning. So the 1/2 times 100 times 2.5 squared. And then we're going to subtract from it the elastic potential energy when we're here. So 1/2 times 100 times 1.25 squared. Okay? And that will give us the amount of energy that's lost by elastic potential energy and has now become kinetic energy. So 1/2 mv squared. So let's see, I've already got this 312.5 for this value calculated in my calculator, so we're just going to take that and we're going to subtract, and we'll do parentheses, 0.5 times 100 times 1.25 squared. And I get 234 joules. So that's the number of joules that has been lost from the elastic potential energy or has been gained and been converted to kinetic energy. So again, 1/2 times 2 is just 1. So I can divide by 1, or I can just then take the square root of this number, and I get 15.3 meters per second. So the velocity right here is 15.3 meters per second. So this makes a whole lot of sense because, you know, we wouldn't be going quite as fast because the force wouldn't be applied for quite as long at this position here. Now, there's one more thing that I want to show you before I end this video, and that's the graphing of this scenario. So if we were extending a spring outwards, right? So this graph would show us x. So x would be 0 here, and we would have our plus x here and our minus x here. Now, this would be a graph, let's say, for potential energy. The letter U is a generic letter that's used for any type of potential energy, so I'm just going to use it here as an example. And then here, let's look at the graph of, let's say, kinetic energy versus x equals 0 and minus x and plus x. So remember, according to our picture, where we have the maximum amount of elastic potential energy is where the x is either the greatest or it is the smallest in the negative direction. And noting that in the equation, x is squared. So our function is going to look parabolic. And if we look here where x equals 0, we know that's where the elastic potential energy is equal to 0. So the graph for elastic potential energy should look something like this. It's maximum, it's the highest at our plus x and minus x, and it goes all the way down to 0, and it looks like a parabola. Now the kinetic energy would actually look opposite, because we know that the velocity is the greatest where x is equal to 0, but its velocity is 0 where it's extended or compressed. Okay? And the v is also squared, so this is also going to look parabolic. So we would have it 0 at our x's, and we would have a maximum number at our position of 0. So these are the two graphs for kinetic energy and elastic potential energy in a spring oscillating.